My name's John Durrell. I'm a lecturer in the engineering department here in Cambridge and also a fellow of Pembroke College. I work on superconductors, which is a very broad area of research, but my primary interest is in practical applications of superconductors. So these are materials which, when they're cooled down to temperatures around about that required to liquefy air, lose all resistance completely. Now the idea is that if we can use these materials in everyday applications like motors or MRI machines or non-destructive testing, we can make them compact, cheaper and more effective. So one particular application I'm working on at the moment is making lightweight motors for aircraft. At the moment, a lot of high-power motors use normal permanent magnets to generate the magnetic field, which is what interacts with the electric current in the motor to make it go round. And the power output and weight of the motor is more or less defined by the weight and strength of the magnetism inside the permanent magnets in the motors. Now what we can do with our superconductors is, if we make them as a sort of lump of ceramic material, we can set currents flowing round. And unlike a conventional solenoid where you have many turns of current, we have one. But because it's a superconductor, once we've set it going round in a circle, it keeps going round in a circle. So what we end up with is something that's effectively like a permanent magnet, but is much more powerful. So to give you an idea, the kind of magnet you'd have attaching things to your fridge will have a magnetic field strength of about 0.1 Tesla. The kind of magnet you'll have in the powerful motors you get in a drone might be getting up towards 0.4 or 0.5 Tesla. The kind of magnetic field you get in a MRI machine for looking inside people is about 3 Tesla or so, whereas the maximum magnetic field we can trap in our bulk superconductors is 17 Tesla. So that's a considerable improvement. And we currently have the world record, as evidenced by our entry in the Guinness Book of World Records for the most powerful superconducting permanent magnet in the world. Some other applications that we're interested in is medical applications. So one of the primary applications of superconductivity at the moment is in medical scanning. And at the moment, if you want to have an MRI taken, you basically have to go to hospital. They have a big machine, it's full of liquid helium, they're expensive, very large capital cost, which means we can't have so many of them. If we could produce large magnetic fields of a high quality using the kind of bulk superconductors I work on, which don't need liquid helium, they can work at much higher temperatures, we could make cheap MRI machines that could go in a doctor's surgery. So if you have a injured shoulder, for example, or an injured elbow, the doctor would be able to wheel this thing out into the middle of the surgery and just have a quick look at what's going on with the soft tissue inside your arm, which is something that's rather difficult to do with other techniques. So what we have here is a polystyrene bucket full of liquid nitrogen, which has cooled these lumps of yttrium barium cuprate superconductor down to 77 Kelvin, at which point they start superconducting. So if I bring the superconductor up to a large magnet, it sets up currents inside the superconductor to oppose the magnetic field, and that holds it in place. And it's not repulsion, because it will actually hang as well. So the magnetic field lines generated by the magnet actually stick inside the superconductor. The other thing people often think about doing with these materials is making levitating trains. Now, there are people who have much more impressive train tracks. I have a very short one here in order to demonstrate the effect. And you can push your superconductor onto the train track, which is made out of superconducting magnets, and you can see that it happily levitates and floats along without any friction other than air friction. So within the engineering department, along with my colleague Professor Cardwell, I run the bulk superconductivity group. And we're a medium-sized group. We have 2 members of academic staff, we have 1 research fellow, we have 3 or 4 postdocs, and about the same number of PhD students. And the work in the group is actually very diverse, which I greatly enjoy. So we have colleagues who work on materials engineering or material science, and they're working out how to make the superconductors that we work with better. Then we have colleagues who are working on characterizing the materials. So they're essentially doing physics. They're taking the superconductors that we've made and they're looking at their physical properties, they're looking at how difficult it is to set up the superconducting currents in the materials, how cold we have to make them before they start superconducting. And there's a close interaction between those two groups. In the last few years, though, we've moved a lot more into applications. So we now have a number of colleagues who are working on taking the superconductors that we've built and turning them into, I wouldn't say prototypes, I think it would be better to say technology demonstrators. Because one of the big gaps when you're trying to take science from the university into industry is the gap between a production prototype and an experiment in a lab. And it's sometimes quite difficult to get funding to close that. So we're spending a lot of our time making something that we can, that in no way, shape or form a product, but if someone comes round from a company, they can see what we're doing, they can understand it, rather than seeing something with pools of liquid nitrogen and it looks like it's been stuck together by Heath Robinson, which is the kind of style you might get in a physics lab. And I think as we've moved towards doing this, this has greatly facilitated our interactions with companies, and we're finding that more and more of our funding is coming from industrial sources rather than from the research councils.